Hello and welcome to the Unit 1 podcast on section 5.3. Today we're going to be discussing electron configurations and some other things as well. I'm Mr. Sakaguchi.
And I'm Mr. Lin.
And let us begin today. There we go. That was weird. Today, one of the major topics we're going to be focusing upon are ground state electron configurations. An electron configuration is just a fancy way of saying we're going to arrange electrons and put them in a particular order.
It's a model of how scientists think where the electrons belong in the big scheme of things.
This is one of the more important things we'll be talking about this semester, and it's something we'll be extending in future units, so know this stuff well. Three rules that govern electron configurations that we're going to be highlighting in the next few slides are the Aufbau principle, Pauli exclusion, and Hund's rule. The Aufbau principle basically says that electrons occupy the lowest energy levels first.
So it's kind of like filling in a parking garage where you park at the bottom levels first until it's all filled up, then you move up to the second level up.
The idea here is that we need to put electrons in their proper spots and also in the lowest energy levels as we move up. The idea here is that you not only have energy levels or principal quantum levels, you also have subshells with multiple orbitals in them. So it's not as cut and dry as it seems. The other idea is that some principal quantum levels will begin before other ones end. And that may not be very apparent based upon this slide, but the next one will kind of illustrate this idea.
Also, later on, you'll notice as we work with the periodic table, the arrangement will make it easier for you to understand the layout.
The Aufbau principle is basically shown here. So the idea here is that no matter how many electrons we have or what element we're talking about on the periodic table, we always start by filling the 1s, as this is the orbital and sublevel that's closest to the nucleus. So we go, and this is just a little trick I show my AP kids. If you line up all the S's, P's, D's, and F's, if you follow a diagonal from top right to bottom left, you can see the exact order of filling. So we would fill 1s, and if we put 2 electrons there and we still had electrons left, we'd go on to 2s. If we had filled that one with 2 electrons, we would continue to 2p. If we had 6 electrons and we filled up 6 in the 2p, then we would move on to 3s and so on.
Realize that the superscripts, the 2's and the 6's for the S's and P's and the D's, etc., that's just the maximum number. So if you have less than 6 or 10 or less than 2, you just fill them in just up to what you have left over. You don't have to write the max number.
The other thing I want to point out here is the idea of principal energy levels beginning before other ones end. So if you'll notice, according to this particular model filling, notice how 4s gets filled before a 3D. So this is the illustrative idea of a principal energy level beginning before another one ends. Another way of representing this is through an energy diagram or orbital diagram that you would see like this, where the S's, P's, and D's are lined up vertically. And you'll also see different overlaps. So for instance, notice how 4s is below 3d, implying the difference in energy.
To help resolve a little bit of the confusion on that, I like to say that the energy level is kind of like floors in a building, and then the D's, even though it's in between, it's kind of like the staircase. They fit in between the levels for the D's and the F's.
Okay. After Aufbau, there's also the Pauli exclusion principle. It basically states that you can put no more than 2 electrons in any orbital, and they have to have equal and opposite spins. In our Aufbau arrow diagram, or orbital diagram, sometimes as it's called, we represent the equal and opposite spins with up and down arrows.
Right.
Hund's rule basically applies only to orbitals with sublevels with multiple orbitals. For PDs and Fs, what you do when you fill with orbital diagrams or with arrows, you're going to put 1 electron in each orbital or sublevel before you start doubling up. So for instance, if we have 2 electrons to put in 2p, they would go in like this, not like this.
Recall that each orbital can hold up to 2 electrons, but even though we've got 3 spaces, or rather the p sublevel has to have 3 spaces. Okay, so you fill in one, then the other. You don't stick them right into the same space. You want to spread it out as much as possible because remember the electrons don't like each other. They are equal charge, so they will repulse each other. So they're going to want to fill out and spread out as much as possible before you go back and fill it back in and double bunk on each of those orbitals.
Keep in mind also that with a lot of elements, when you get near the end, when you're running out of electrons, you'll often end up with empty orbitals or sometimes orbitals with only one electron in them.
And that's totally normal and okay.
Yeah, so don't feel like they all need to be filled up. Okay, so there are two basic flavors, oh actually three flavors of electron configurations. One we don't use that much. One idea is this orbital diagram. Orbital diagrams use up and down arrows. A lot of times you'll see boxes representing the orbitals. Sometimes you'll see underlines. Other times you'll see circles. And then the arrows are ubiquitous. Sometimes you'll see them written like this, where they're all written in a line. The implication is that the linear order kind of indicates the difference in energy.
Right, and the further you go to the right, the higher the energy level.
Some other cases you'll see the same orbital diagrams represented like this on the right, where you see up and down arrows in that vertical representation of these sublevel orbitals. Another way to do these diagrams is using this shorthanded notation or electron configuration notation. So notice that what you see here in this lower part represents the arrow diagram for vanadium. What happens here is what's in the arrows is represented by the superscript, and then the 1s indicates the principal quantum level and the sublevel type. This is not algebraic, so it doesn't mean 2 times s. It means quantum level 2, sublevel type s, 2 electrons in that sublevel.
Not squared or to the 6th power.
Right, and we'll continue all the way until we run out of electrons. One other thing to note is that occasionally when you write in this notation, the Aufbau order is not implied. So in reality, we know 3D actually gets filled last, but because of the wanting to put the principal energy levels to group together, you'll sometimes see these configurations written in this fashion. So please don't be confused by that. They're not disavowing the Aufbau order, but basically they want to keep all the 3s together.
And that's just up to the publisher. In at least in my classroom, your classroom too, we'll be doing it where it'd be written as 4s2, then the 3D3.
Well, we would accept either one.
Yeah.
But just keep in mind that some textbooks do it this way. Other textbooks will put the 4s2 before the 3d3.
Mm-hmm.
There's also the third notation, which isn't used a whole lot, but it's noble gas notation, and this is a method by using noble gases as a way to kind of eliminate certain configurations.
It helps to reduce the amount of writing, but more importantly, it helps show up the it helps show what we're going to call later on the valence electrons, and they're the outermost electrons, and those are the ones that actually interact during a chemical reaction. So the ones that are innermost really don't do anything at all. So as a result, they kind of just leave that out, and they wind up being represented by the noble gas. So for instance here, Ne put in brackets, neon, actually can represent 1s2, 2s2, 2p6 as shown on the periodic table. Okay, so then you wouldn't have to write that all out. Or in the example down here for nitrogen, they don't write out 1s2, they just do helium, and that helium substitutes the 1s2. And then you have the remainder of the electron configuration of 2s2, 2p3, and that would be this portion here. Okay, and that's the outermost energy level, and it's the most useful part of the electron configuration.
Now note for this example, putting helium in square brackets doesn't really save you a whole lot of writing, but for larger elements with bigger atomic numbers,
like 60 something,
this is where it becomes a lot more convenient, and this is something we'll practice in class.
Right.
There are many exceptions to configurations. The rules basically work up until we begin to get into the fourth period or third principal energy level. And basically what happens at this place, because you have the D sublevel, you start getting exceptional configurations that do not follow Aufbau, Pauli, and Hund. And this also explains why some elements have more than one stable configuration, which will become more important in the future podcasts and future units of the course.
We're not going to make you memorize these exceptional elements, but just be aware that they do exist.
And this is mainly due to the closeness and energy of DNS sublevels. So you'll see them kind of do
Blur.
some bizarre things that don't make a whole lot of apparent sense, but they are useful for our purposes. In our last slide, we're going to talk a little bit about valence electrons. These are the outermost electrons, as we talked a little about earlier. And the reason why we care about valence electrons is that we're going to find that a lot of the elements and ultimately compounds, chemical and physical behaviors can be directly related to the valence electrons. These are in the highest occupied energy level generally. Usually we're only going to look at S and P occupied sublevels. Even though D is there, we usually don't count those.
Also, don't forget that D is also one energy level lower anyways, so
That's where it gets a little hazy.
yeah.
This is another area where the noble gas configuration shines because it's easy to determine numbers of valence electrons. So notice how we have basically for these configurations, you're looking for the highest occupied principal energy level. In this case, it's level 3. So we have 2 electrons here, 4 electrons there, which represents 6 valence electrons for sulfur. For cesium, it would just be 1 valence electron. And we'll talk about the importance of these valence electrons in our next unit.
Right.
Another way to represent valence electrons is using something known as an electron dot structure. Sometimes it's called a Lewis structure. Basically what we do here is we have our element symbol, and then we use the valence electrons, we surround the symbol with dots. Usually we put 2 dots on each of the 4 sides of the symbol.
Right, and so in this example, phosphorus happens to have 5 valence electrons, so it just gets 5 dots around it. Simple as that.
And I believe that ends it, so
Yep.
until next time.
That one.